Welcome everybody to day 5 of the Organometallics class. Few quick reminders. So I have the syllabus up because I want to remind everybody that some of you have already sent me and the TAs your suggested or your proposed topic for the Wikipedia article. Thank you for those who have done that. For those who haven't, reminder that the deadline for picking a topic is on Thursday of this week. And this doesn't need to be, I guess what I want to say here is that this doesn't need to be, you send the email and that's the final topic we decide on. This can be more interactive, more iterative. So if you think about a general area that you're interested in, then you can let me and the TAs know and we can help you refine that or help you pivot to something that's going to be more straightforward, more productive to do. But we can't do that if you don't engage with us. So if you have some ideas in mind and you want to bounce those off of us, please do that over email or see me or the TAs after class. But that's coming up on 4/20 as the deadline for picking the topic. We also have a homework that was sent out over the weekend, and I'll leave it to Camille to say a few points about the due date and the office hours for that homework.
Yeah, it is due on Friday the 28th, so 2 weeks after it was assigned, either over email or in person to me or Nathan. And we are having 2 office hours for it. One is one is April 21st from 11 to 12 in the conference room, and one is April 27th from 3 to 4 in the 4th floor conference room. So check your schedule to make sure you can make it to 1 or 2 if you feel.
Thanks, Neil. So one point I want to emphasize about the problem set is that maybe like you've seen in other classes at Scripps, the problem set in this class, the problem sets are not designed to just be straightforward regurgitation of course material. They're designed to push your horizons a little bit, expose you to new content, expose you to examples that are a little bit off the beaten path. So with that in mind, I think it's important that you take a minute this week and page through the problem set and flag ones that you know how to do and others that you might want to ask about during the office hours. That's the spirit of the problem set. So if you're trying to wait till the very, very last minute and do it on your own, then that's going to be not a super pleasant exercise. And this comes from somebody who always is a procrastinator. So don't put yourself in that situation. Take a look through it now and get oriented, and then take advantage of the office hours to ask questions and get those questions clarified. Any other logistical points, TAs? All right.
Just reiterate that everything's online.
And everything is online. All the course materials are online. I think we maybe don't yet have a PDF of the problem set online, but I'll put that online today, so everybody has that as well. All the course videos are online, and the problems of the day and handouts are also on the course website if you don't want to use Canvas. Were there any questions about administrative details? Okay, as a reminder, last week we concluded Thursday's class with a discussion of ligand substitution. So specifically, we talked about the 2 canonical mechanisms, associative and dissociative. And then we left the class with a discussion of the Engle effect as it manifests in this recent literature example from the Pribenow group. We had talked about associative ligand exchange, introduced that, and now I'll introduce its counterpart, dissociative ligand exchange. Associative ligand exchange is commonly observed with 16 electron complexes, if you remember last class. dissociative ligand exchange is commonly observed with 18 electron complexes. This makes sense intuitively because if you imagine a hypothetical associative ligand exchange with an 18 electron complex, you're at 20 electrons, and that is not going to be favorable. So I think this follows from common sense. So an 18 electron complex will lose a ligand, get down to 16 electrons. In the case of an octahedral metal, there'll be potentially some geometric reorganization from an octahedral complex to a trigonal bipyramidal complex. This can then associate a ligand to get back to 18 electron complex. So the important thing here is that there is a implicit step that's not always drawn that involves losing a ligand before you gain a ligand. And a classical technique for disambiguating between these two possible mechanisms, associative versus dissociative, is to take advantage of the differentiated rate profiles that these two processes exhibit. And so let's unpack that briefly here. So in the case of a dissociative pathway, the process, as we said, begins with loss of a ligand, and loss of that ligand is typically the rate determining step. It is slow, and subsequent capture of that vacant coordination site with a new ligand is fast. So based on that, what would you expect the rate law to be? Does someone just want to shout it out? Okay. The rate will be what? 1G?
K times the concentration.
Yep, okay. First order kinetics, and there's positive rate dependence on the concentration of the parent complex. And then subsequent trapping step is fast, so that second incoming ligand is not seen in the rate law. You can also imagine that because this initial dissociation loss ligand is slow, if you were to add exogenous of that same ligand, the outgoing ligand, bless you, that can be inhibitory in this process. You can have negative order on the outgoing ligand, and we will see how that manifests in an example in a moment. Okay, and then the other possibility is associative ligand exchange. So here it's a different scenario. Now the slow step is association of that incoming ligand, and then loss of the outgoing ligand is fast. So the rate law in this case, Madison, is what? It will be dependent on the concentration of the parent complex. And then how would it be different than? Perfect. So the rate determining step is association of that ligand. That's a bimolecular event. So we would expect that incoming ligand then to, the concentration of that incoming ligand to appear in the rate laws. We have overall second order kinetics, positive order dependence on both the incoming ligand and the parent complex. Any questions on that?
Curious, that's
Yes.
LNM L prime complex intermediate reaction.
In the case, the associative pathway, the LNML prime species is a intermediate as considered here.
So there's one more vacant coordinate site on the M for the L prime.
Right. So that's why in the previous class we said that associative pathways typically are 16 electron. Okay, so let's now consider problem of the day number 3 from last time while we wrap up that worksheet. So let me share that. So this is your day 4 worksheet, problem of the day number 3. In this case, the process that we're considering is this tetrakis isonitrile cobalt complex that is undergoing a ligand exchange process with an incoming molecule of phenylacetylene. So this question has a few parts to it. Part one is to, for both the starting material and the product, go through our normal flow, coordination number, oxidation state, electron count, and overall electron count. B, then provide possible mechanisms for the ligand exchange process that will fall out directly of the preceding discussion. And then C, design a set of experiments to distinguish among these possibilities from part B. And here, I think, try to think through the details of this experiment, not just say, I'm going to use this technique, but actually what specifically are you going to, what variable are you going to change? What's the effect that you expect to see, et cetera. So let's take a couple minutes to think that through, compare with your neighbor, and then I'll call on volunteers.
Oh, no, he didn't.
All right, are we ready? Okay, let's at least get A and B up on the whiteboard here so that we can make sure the discussion is properly oriented. So pay, is it patient? Pay, or do you prefer Cindy? Okay. Cindy, what about the electron count for the starting material and product? The coordination number? You said 4, okay. Sorry, I didn't hear you. That one's straightforward. And then what next? Oxidation state. We have cobalt only L-type ligands, so we're going to say that's 0. That makes the d electron count
It's 9.
9. And the overall electron count then is 17. And immediately you might be thinking that seems uncomfortable. But that's the elegance of these very bulky isonitrile ligands, is that they block other things that could normally happen from happening. So you might imagine 17 electron cobalt 0 complex might like to form metal-metal bond to get to 18 electrons, but those bulky ligands prevent that from happening. So you have an unpaired spin. The complex will end up being paramagnetic, but it is stable in the 17 electron state. And then the key point is there's no change in the overall electron, these parameters from starting material to product. Super, Cindy. Okay, that's A. B, I think B and C, maybe we can tackle together here. What do you think, Annabelle?
I think it's more likely to be dissociative because the ligand is bulky.
And you're saying you favor associative because of the steric bulk of the, as you said, dissociative. Sorry, did I mishear you? Dissociative. Okay. Because of the steric bulk of the ligands. And then C, now we can test between these competing hypotheses. How would you do that?
Since the rate wall is different, I think we can test the concentration of time ligand impact on the rate.
Okay.
I think we can maybe use Lewis portion to test the formation of the complex.
Love it. Okay, so we're going to monitor kinetics here by UV. So I think Annabelle's picking up on the fact that it's paramagnetic. NMR is probably not going to be a great choice. So, but the complexes are colored, so UV could be a good choice. And I'm going to give you some data here, Annabelle. And then you said you want to first, or one of the things you want to do is change the concentration of the incoming alkyne. Is that right?
Yeah. So
let's do. I will show you some data and then you can react to this data. So if we vary the alkyne equivalent, so these are under pseudo first order conditions, hence a large excess of alkyne. We're going from 10, and I would normally just present, in the papers, people like to present these in terms of concentrations, but just for the sake of clarity here, I'll present it in terms of the equivalence. So 1.41 times 10 to the minus 3 per second, 10 equivalents, 3.29 times 10 to the minus 3 with 20 equivalents. So from this, you would conclude what?
it is associated.
The reaction is running faster with higher concentration of the incoming alkyne. So we would conclude from this associative. But what if you still weren't really convinced with this? Could you do another experiment to further support this? Any ideas from the class?
Is it possible to try to isolate that's associated? Even if it's for 5 coordinate columns.
You could, but if that is would need to be stable. In this case, it would be a 19 electron species. It's probably high energy relative to the starting material in the product, so it might be difficult.
If you add more of the other ligands.
Aha. What we just talked about, you can add let's start with these 10 equivalent alkyne conditions, and then we can add excess outgoing ligand, and we would expect this to be accelerate the reaction or slow down the reaction.
I think it was an associative process and you added more of the excess ligand, it would slow down the rate.
Okay, so we can do this experiment. We're just going to borrow these conditions. Whoops. For the first. And then 20 equivalents. And we see pretty similar rate. Modest increase, but you'd say with some potential for experimental error, this is looking pretty similar. Any questions on that? Okay, a few more points on ligand exchange, and then we'll do one more example, then wrap this up. As I mentioned before, just before I move away from this slide, for the organic chemists in the audience, you might recognize some parallel here between associative, dissociative versus SN2, SN1 processes in main group organic synthesis, and I think this connection is not lost on me either. They're not exactly the same, but they have some parallels. So if that helps orient you, you can think in those terms. So another point now in the case, let's consider this molybdenum hexacarbonyl complex. Metal carbonyls in general, they do not undergo exhaustive ligand exchange. And there's a reason for that, which is that when you're bringing in let's say a phosphine ligand, for example, each outgoing CO ligand makes the remaining CO ligands that are pulling electron density off of the metal through pi back bonding more and more important. So in a hexacarbonyl complex, you can imagine there's this six-way tug of war going on where all of the carbonyls are pulling for electron density. But as you remove some of the key players from this tug of war, now the remaining ones are increasingly strongly bound. So they will not undergo exhaustive substitution. In most cases, there are some exceptions to this. For example, as we talked about in our labs group meeting, nickel carbonyl will typically undergo exhaustive ligand substitution, but that's more the exception than the rule. So we can consider this case of the molybdenum hexacarbonyl now. And there are two possible, if we consider introducing an excess of a phosphine ligand here, it will undergo triple ligand substitution. And you'll see there are two possibilities where those ligands can go. And this will allow me to introduce some stereochemistry terminology. So does anyone want to predict which of these might be favored?
Facial.
Okay, so the two possible stereoisomers here are described using the terms FAC, and maybe it's FAS, I don't know, FAC, I always say FAC, and MER, so facial versus meridinal. And Shenghua is saying he favors the FAC isomer in this case as the major product. And why do you think that, Shenghua?
The strong trans influence of phosphine ligand will this favor two being trans to one another as in the meridian?
Aha, perfect introduction to the next part of the class. So so Shenghua is invoking here the trans effect. And if you're not familiar with that, we will get to that shortly. So thank you, Shenghua. Any questions on that? Okay, let's now consider problem of the day number 4 from the previous worksheet, and we'll wrap that up. So I'll pull that up quickly. And I've redrawn the key reaction that we're considering here. So the transformation in question, or the process in question, is treatment of the NC metallocycle with 4 carbonyl ligands. Manganese, I have it misdrawn, manganese as the metal, with 2-phenylpyridine. That, as I've drawn here in toluene and under photo irradiation, is going to form a new species A that will then further get converted to another new species B. So provide those products, explain the role of light in the reaction, and then let's say your lamp is broken, but you still wanted to get the same product. How would you possibly consider promoting this reaction based on your answer to B? Okay, Jalen, what do we think here for A?
I'm not sure. Maybe I need a few minutes more.
Okay, take a minute to think about it. All right, Jalen, what do you think?
So I think the phenol group will do some kind of rotation and kick off 2 carbonyls.
Okay, so let's break this down first. If I were to tell you that let's not consider the 2-phenylpyridine first and just photo irradiate this starting material, what might you expect would happen in toluene as solvent?
It could go some.
So what is the light potentially going to do?
I think it's gonna turn the phenol group there to turn it to a 4 or 6 electron donor.
I see.
Use a pi electrons to do the coordination.
Okay, I think you're maybe getting ahead of us here. Any assist from the audience? Photo irradiation of that tetracarbonyl complex will do what?
So one of the facial carbonyls should be most likely to be activated now.
Okay,
So
and then
then you could
what would
discuss
happen?
if either like the pyridine, like nitrogen, is gonna coordinate to the manganese or the solvent.
Okay. And which would you prefer, Philip?
Well, because it's like completely, like the solvent is basically everywhere, I would say that maybe the solvent is coordinating first, and then it will, like the ligand will exchange with the pyridine
Okay, beautiful.
later on, because it will have like stronger binding, I would assume, than just plain taurine.
So we apply light, we photodissociate a CO ligand. This is a trick that we'll talk about in just a moment. Then we have an open coordination site. We have a large excess of solvent, so a solvent molecule can coordinate and we can observe it. It's a high energy intermediate, but we can observe it spectroscopically. And then do you want to take us home, Philip? What would happen next? So this is A. And then B would be what?
So I would assume that the pyridine, like the pyridine is basically gonna kick out the 12.
And anything else you want to happen?
I mean, potentially, you could assume that you're gonna do like CH activation on the phenol ring. So you would activate it and take out another carbon. But I think from what we've seen before, the partial should be like more stable. Yes.
Okay, beautiful. So you could imagine these, I think what Philip is saying is these CH bonds would look tempting to activate, but in this case, we don't have a carboxylate base. We don't have some of the signaling elements that we would normally look for in a CH activation process that we'll talk about later in class. So it would happily just exist here in the now newly ligated state. So this is an example of a photo-assisted ligand exchange. If you're interested in reading more about this, we'll send this paper out. This is an ASAP article from the groups of Lynham and Fairlam in the UK. Okay, so this, any questions on this problem? This kicks off this short section here that we have on how to encourage ligand exchange. Oh, sorry, there's one more part of the question wasn't there. C. So C was if you have no UV lamp, what would you do with this product?
Heat it up.
Heat it up. Okay. Beautiful. Anything else?
Ball mill, maybe?
Ball mill. You provide, yeah. Find a way to introduce energy. So mechanochemically or thermally, heat is a good first thing to try. So these reactions are done under ambient conditions, the photo-assisted ligand exchange. So the first thing you try is just heat it up hotter. Okay, so ways to encourage ligand exchange. Just we'll consider a couple general types here. We just covered this one of photo-assisted ligand exchange. We've done this in our lab before with tungsten carbonyl. Ligand exchange to put on nitrile ligands, for example. So, that's a common technique that you'll see several times. The origin of that is quite interesting. So you can imagine, as we talked about before, the overall bonding picture of these organometallic complexes. You have a d electron that is capable of being excited to a higher energy orbital, for example, a ligand-centered antibonding orbital. That then destabilizes the bonding interaction between the metal and the ligand and allows it to dissociate more readily. Other processes that we can take advantage of to encourage otherwise recalcitrant ligand exchange, a common one is using silver salts. Or other metal salts work well for this too, but silver is a particularly powerful one because silver halides are insoluble in most organic solvents, so they will crash out and drive ligand exchange through Le Chatelier's principle, pulling this potential equilibrium to the right. So a lot of these reactions are potentially reversible. So it's a matter of finding a way to push it to the right. With metal hydrides, one of the concepts that we will cover in the class is that metal hydrides can be hydridic or protic. In the case of a hydridic metal hydride, then you can protonate the hydride off to generate H2, which then can leave the flask if you're sparging it, for example, to open a new coordination site. We talked about photoassisted ligand dissociation. We can also encourage ligand exchange through transmetallation, a concept we covered in the context of our discussion of chemistry, and that we'll talk about in more detail in Thursday's class. So in this case, we're generating, in the specific example shown here, we generate a magnesium halide salt that's going to be in some cases insoluble in the reaction medium, in other cases just a strong thermodynamic sink. And that can allow us to exchange an X-type ligand, for example, a halide with now an alkyl ligand. And that same principle can be applied when rather than a metal aryl or metal alkyl, you're talking about a metal hydride. So you can transmetallate, in this case, to generate from a metal X starting material a new metal hydride, taking advantage of formation of a stable salt as a product. Any questions on that? Okay, let's shift gears now to the concept that Chenghua introduced to us, which is the trans effect or trans influence. And sometimes in the literature, these terms are used interchangeably. Sometimes in the class, I will probably confuse them and use the wrong one at the wrong time. But strictly speaking, the trans effect refers to a kinetic phenomenon. So we read that out in terms of product selectivity. So in a ligand exchange, we just covered one example where ligand exchange could potentially give you two stereoisomers. And the trans effect, along with its sibling, the cis effect, will allow us to predict which isomer is likely to be the major product, and that ultimately reflects kinetics. Now, related to that, and sometimes acting in the same direction, is the trans influence, which is a thermodynamic descriptor. So when we think trans influence, we're talking about ground state phenomenon, such as bond shortening, bond lengthening, back bonding interactions that we can read out by IR. And the trans effect and influence are particularly important for understanding and then predicting ligand exchange events in D8 square planar complexes. And so let me define this trans effect. Like some of the other concepts we've seen in class, the trans effect is an empirical trend. And it is an empirical trend that varies slightly from metal to metal. So depending on what experiment you do, you might get a slightly different order. But the general trend is the same. So if you in a different class have seen a slightly different order, that's probably because the metal that they used to make that determination was slightly different than the one here. But the list I'm providing here is directly out of the Crabtree textbook. The original reference is shown here. I believe this is for a series of platinum complexes. And so the trans effect describes this phenomenon that some ligands are more effective than others at labelizing ligands trans to themselves. And so I've tried to depict that here. The ligand in question, this trans influencing ligand, is the one that's highlighted with the pink ball, and the outgoing ligand is the ligand shown as denoted as X. And so the empirical trend is shown here, and the general features to remember are that ligands that have strong influence, you see there's some parallel actually to the spectrochemical series, but it's not exactly the same. So the ligands that have the strongest trans effect are those that are typically strong sigma donors and pi acceptors. And those that have the weakest trans influence are typically pi donors. And weaker sigma donors. So that's the general trend to remember. So bless you. So Shenghua was invoking the fact that the relative trans influencing nature of CO versus phosphine in his explanation. You can see the relative effects that they have here. So this is the empirical trend that we'll expect you to remember. And if in an exam, we would try to give you extreme cases rather than near neighbors where it might not be obvious. Now, the origin of this empirical phenomenon is more complicated, and try to bear with me as I explain it. If it's not clear, you can always ask me after class. But as a heuristic, as something that is, I think, helpful to maybe have an intuitive grasp of this, if you imagine the trans-influencing ligand and the outgoing ligand as bonding to the metal through a shared orbital, then the trans-influencing ligand that is engaging in very strong bonding through strong subordination, strong pi accepting, that's dominating the bonding interaction and weakening the bonding interaction to the outgoing ligand. So that's a heuristic that you can use to help remember. Now, the actual underlying scientific explanation is a little different from that, or a little bit more granular than that. And that is that in a 16-electron complex, it's undergoing ligand exchange through an associative pathway. And when you associate the ligand, then the new geometry will be trigonal bipyramidal. And in a trigonal bipyramidal geometry, the equatorial ligands, the equatorial positions are particularly pi basic. So it's very stabilizing to have a pi accepting ligand at a pi basic position. And based on the principle of microscopic reversibility, the outgoing ligand, the trans-influencing ligand, and the incoming ligand should all, bless you, be on the equatorial positions of a trigonal bipyramidal. And you want that trans-influencing ligand to be pi accepting, if possible, and not pi donating. And so that's depicted here, where in the preferred trigonal bipyramidal geometry, you have all of those ligands around the equatorial, and that ends up leading you to this the trans-influencing ligand destabilizing, labelizing the outgoing ligand in question. So let's consider one classical example here, and some of you will immediately recognize this. If you don't, if you haven't seen this before, if you have seen this before, it's just review. But if you haven't seen it before, it's like I feel legally obliged to present this as an organometallics instructor, because every organometallics class I've ever taken has shown this as the classical example of the trans effect, and that's shown here. So we're going to do a series of ligand exchanges from this platinum to tetrachloride complex. Manage to end my screen share. Okay. Just applying the trans the trans effect that we just learned. So let's walk through this. In the first ligand exchange, we react with one equivalent of ammonia, and that one, any position that exchanges ends up being degenerate. So there's no selectivity issue to consider here. And then now this should be 1 minus, is that right? And then we'll take this one step further, one more equivalent of ammonia. And now, Elin, what do you think is going to happen?
The chloride have like a stronger trans effect than the ammonia, so we will finally like place have both one like form like a cis.
Okay, so we try to find which ligand is going to be the most strongly trans-influencing, and you said it's which? Fluoride. Okay, so we have two potential positions. Let's just orient everybody. So we have two potential positions to exchange. We have these two positions are equivalent, and then this position. And you're saying that the chloride, you see one of the positions is trans to NH3, one of them is trans to chloride, and you're saying, and I'll try to use the same color coding I did, that the chloride should be the trans-influencing ligand here, and we should, then the incoming ligand, what coloring system did I use here? Green. Incoming ligand is shown here. Outgoing ligand is light green. And the product, the name, Elin, is what? Cisplatin, classic example of a organometallic coordination complex used actually as a human therapeutic. Super. Any questions on that? Okay, so now let's cover the related phenomenon, the cis effect. And the way to remember the cis effect, which is most relevant to consider now with octahedral complexes and 18 electron, is that it's more or less the opposite situation of the trans effect ligand. And that would be very confusing if that weren't the case, right? Because you have some ligands that are cis, some that are trans, and if they have the same influence, that would be very confusing. So the cis influence, the cis effect is functions effectively the reverse of the trans effect. But there are some exceptions that, or some cases where there's a little bit more subtlety involved that are worth unpacking. So some of the special cases to consider, let's look at the ligands here that have the most pronounced cis effect. And are there any shared features of these ligands that that stand out? Any thoughts here?
And either be quantitative or quantitative.
Acetate, formate we have here. And why would that be important, Wenji?
Is to have a extra coordinating atom. I would guess there's some sort of vicinal effects that those ligands can do on the complex.
Aha, so you can toggle from kappa 1 to kappa 3 through chelation now, and that can be, you can access a chelated structure as a low energy pathway for this overall ligand exchange. So one point to layer on to this analysis that it's opposite of the trans effect is that chelating ligands have a special role when you think about the cis effect due to the potential for chelation. So the overall trends here, let me just complete these series of notes. The cis effect is stabilized by bidentate ligands or bidentate coordination. Destabilized by strong sigma donation from X. and also destabilized by strong pi accepting character. Okay, let's apply now what we just talked about, the cis and trans effect, to a specific case study. And that will be problem of the day number 1 for the day 5 worksheet. So I will share that. So this is a ligand exchange process that we're asked to consider between manganese pentacarbonyl with one halide ligand and triphenyl arsenine. And if you haven't seen this before, this just think triphenylphosphine. This coordinates and behaves just like triphenylphosphine. So we need to predict the product or products, think about what the mechanism would be, propose a mechanism, and then order this series of complexes, iodide, bromide, chloride, in terms of expected reaction rate. So I'll give you a minute to think about that, compare notes with your neighbor, and then we'll discuss as a class. Oops, I wasn't supposed to put these up. Cover your eyes if you looked already. All right, let's get A down, and then based on that, we can take another 30 seconds to think so that everyone's on the same page here. So Jenny, what do you think for A?
I think because the complex is 18 electrons, so it should be dissociation.
Okay. And then what do you think the product is going to be?
The incoming ligand will be, I don't know how to describe it, but it should be like the left corner.
The left corner. So are you talking about this one? Okay. So what are the, let's just back this up. So what are the possibilities? You have 3 potential positions you could exchange. You could exchange the halide. You could exchange the, let's call this the cis carbonyl, the carbonyl that's cis to the halide, or the trans carbonyl. And the cis carbonyl, you have 4 of them that are equivalent, right? So how did you reason through which one would exchange? Jenny's answer is this. And how did, maybe can you explain your reasoning? Jenny? Okay, the cis effect, you're saying that the cis effect of the chloride, iodide, or bromide, they're all stronger than CO. And they should guide exchange to the position cis with respect to themselves. Okay, and then we'd also say if you want to consider the trans effect, the exact opposite is the case. So that would vote against the trans CO. Now, here's an interesting question for you to consider. I don't know if you considered already, Jenny, but why not exchange the halide ligand? Draw that out. Why not this? What makes you unhappy with this? Any assist from the audience? What from the rest of the class? Anything that feels uncomfortable about this?
We're using chloroform. It's not like, I think it could be favored in some protonic solvent, but not chloroform.
Okay, and why is that?
You cannot stabilize the product, basically the halo ion. So
Great, so the product is charged, it's cationic. So in a solvent of relatively modest dielectric constant, we'd expect it to not be stable. And though we tend to think of phosphines as, or sorry, carbonyl ligands as being pretty strongly coordinating ligands, remember the discussion we had earlier, that the more carbonyls that you have, the more destabilizing it is. So the complex is actually happy to lose a carbonyl, so it can gain a strongly sigma donating arsenine ligand, and now engage in even stronger back bonding to the remaining carbonyl ligands. Great, okay, and super, Jenny. And Madison, how about part B? Do you want a minute to think about it, or do you already have that?
Is gonna have highest, right? Or like it'll be like the fastest, I think.
Okay, let's go up to our, so what do we have to consider here? Now, go ahead.
It has a stronger trans effect and will be
Okay, so let's look at the cis effect series here.
because it has a weaker cis effect.
So you're saying iodide will be the slowest and bromide then chloride.
That's what I mean.
Let's put some numbers there. Beautiful. So it's about an order of magnitude as you go up this series. Or, good. Any questions on that?
Their size or just it's just the empirical trend.
It's an empirical trend, but then it if we're talking about their actual properties of the ligand, size and polarizability is part of it. I think the general descriptor here we would say is thinking about this pi donation strength and the relative, the sigma donation strength and the pi donation strength. So we know that in general, you're going to have stronger sigma donation when you have when you go from chloride to bromide to iodide. You've got bigger, more diffuse orbitals, more electron density, and so that goes hand in hand with size, but size is not the dominant feature per se. Okay, before we wrap up this discussion of ligand exchange, just one more piece of terminology, and that is the terms that you'll hear in talks and in the literature of spectator versus actor ligand, or ancillary ligand versus reactive ligand. So this is just a point of nomenclature that you can jot down. So spectator ligands are those that remained unchanged throughout the course of the reaction. They're those that are said to be kinetically inert. Now they can have a crucial role in modulating the electronic and steric properties of the overall complex, but themselves, they're not engaging in the action. Actor ligands, it's the opposite situation. So they are those that are undergoing ligand exchange and those that are getting modified during the course of the reaction. So let's just consider one case study. So this is an example of alkyne trimerization, something that we'll cover later in class. And so in this case, the CP ligand is a spectator. It's playing an important role in modulating steric electronic properties, but itself is not involved in the action. The first step will be loss of one or both of the phosphine ligands. And so those are defined as actors. And then the alkyne ligands that coordinate, of course, those are also actors because they're actually undergoing chemical transformations. Okay, so now let's jump into a discussion of oxidative addition. So we're shifting gears now from the simplest processes, which are the ligand exchange events, to now getting into the meat and potatoes of, or if you're a vegetarian, the tofu and potatoes of organometallic reactivity, which is the steps that involve bond making and bond breaking. So the first we'll cover is oxidative addition. If you like arrow pushing, which I know most organic chemists do, you can push arrows like this. So oxidative addition is defined as the metal mediated breaking of a substrate, typically sigma bond, and then formation of one or two new metal ligand sigma bonds. And so it involves pushing electrons from a filled d orbital on the metal to a pi star antibonding orbital on the ligand. And when you think about that mechanistic character of the reaction, then that defines some of the points I'll make here. So the metal, of course, then must have the electrons. We talked about how D0 metals cannot engage in pi back bonding, and thus by definition, D0 metals cannot engage in oxidative addition. The metal needs to have a vacant coordination site to allow the substrate to bind to engage in this electron transfer and bond making, bond breaking process. Because of how the electrons are flowing from the metal to the ligand, you might predict a priori that there are some features of the rest of the surrounding ancillary ligands that favor oxidative addition. That includes those ligands being electron donating and sterically small. So you'd imagine an extreme case would be like trimethylphosphine. That's very sigma donating, very small, and that's a great ligand for oxidative addition. It might not be a great ligand for other steps in your putative catalytic cycle, but it's a great ligand for oxidative addition. And then some of the consequences of oxidative addition are that, as you can see up top here, the metal oxidation state is increasing by 2 typically. And the coordination number is also increasing. And as we just talked about, strong sigma donors are good ligands. Relatively few pi acceptors. So we talked about these polycarbonyl metal complexes. Those are not great ligand. Those are not great complexes for oxidative addition because they have so many pi accepting ligands, and then ligands that are sterically small. So we'll now cover first substrate classes, categories of substrate classes that engage in oxidative addition, and then we'll unpack the mechanisms. I think in the Hartwig textbook, the way it's organized is substrate class and mechanism, substrate class and mechanism, but here we'll just go put all the classes up and then we'll show all the mechanisms, and you can connect the dots of which goes with which. So the three general substrate classes, and these are probably not completely all-encompassing, but these are the general classes. The first class we'll consider is the nonpolar class. So these are AB bonds where neither A nor B are highly electronegative, and the overall reagent is not a strong oxidant. So consider here examples like H2, like silanes, like CH bonds, and then heteroatom H bonds, thiols, amines, etc. So when we look at these, we say these are not very oxidizing, and the bonds are not very polarized. These nonpolar oxidative additions will typically require a vacant orbital adjacent to where the ligand is binding to the metal, and that has to do with the mechanism involved, as you'll see in a moment, that the two atoms in this bond end up being oriented cissoid to one another in the product. So the next class to consider are AB bonds, where either A or B is highly electronegative, or you just look at the complex, you look at the reagent and you say, that's an oxidant. That's a chemical entity that we know is electron poor and desires electrons. So these are things like dihalogens, organohalides, including alkyl and aryl variants, and HX. Sometimes people will consider this to be its own class, so like mineral acids. I loop it in here because I think a lot of the features are shared actually in terms of the rest of the polar category. Now, an interesting difference between polar versus nonpolar is now you don't need a vacant orbital at this adjacent position like you did above. And that's because the mechanism by which it can take place, you have more options than you did in the nonpolar case. So it could engage in what's called an SN2 type pathway, where you first break the AB bond, B is lost as an anion, and then reassociates the metal at a later stage. So it's an asynchronous mechanism, whereas the nonpolar are typically engaging in synchronous. When the metal is starting material is 16 electron, then both A and B coordinate in the product. We'll also consider cases where the starting material is 18 electron complex, and in that case, only one of A or B will coordinate, and the one that coordinates is normally the one that is the strongest binding. And then the third category are molecules that typically are containing AB multiple bonds. And in that case, not all of the bonds between A and B are severed upon oxidative addition. So we call these AB intact category. And so some of the ones that you might already be familiar with are shown here. So O2 and oxidatively add first, it will coordinate, well, O2 is coordinated, capable of coordinating in a bend end-on fashion as well as a side-on fashion. When it coordinates side-on, it can undergo octave addition to give this three-membered ring structure. And then pi bonds, we talked about how in an extreme case, pi back bonding can actually result in metallocyclopropane character. The same is true with alkynes, that you can, with extreme back bonding, you can have metallocyclopropene character. So we'll just look at that example here. And this is a continuum depending on how strong back bonding is. So octave addition is an extreme case of back bonding where you back bond it so strong into the pi star or the sigma star antibonding orbital, or in this case, the pi star antibonding orbital, you actually rupture the bond. And the classical cases of octave addition are monometallic, but there's been an emerging exciting literature, particularly in the past 15 years or so, of multi-metallic octave addition processes, which are mechanistically related but have some distinct elements. So just in the spirit of giving exposure to some of the modern research threads in the field, I'll introduce these briefly. The key idea here is now not all of the oxidation state changes and all of the bond form and bond breaking need to be localized to a single metal. They can be divided between the metals. Typically, these are bimetallic. You can imagine, in theory, you can have higher order complexes, but it just becomes more and more complicated. So let's consider now a couple cases of this of these bimetallic type octave additions. So one flavor of that is that you have a metal-metal multiple bond, and the AB molecule is adding across that metal-metal multiple bond, changing the oxidation state of each of the metals by one and forming a new bond to each of the metals. And these can be either of a homo bimetallic flavor, meaning the same metal, or a hetero bimetallic flavor, meaning the left metal and the right metal are different. And then you can also have a case where the metal-metal bond is a single bond, and then upon octave addition, which if it's purely concerted would be a five-membered transition state, or sorry, four-membered transition state, but can also be more asynchronous in nature. Now you rupture the sigma-sigma bond between the metals and form one new bond each to the AA or AB. So in this case is the simplified case, or dihydrogen, for example. So you have a homobimetallic species splitting dihydrogen into two metal hydrides would be one example. So let's consider two actual examples from the literature. And so the first one is from this paper here, and this will bring us to our chemist of the day, who I'm sure some in the audience recognize his photo. And how you're smiling.
It's Ueda from Purdue.
Chris Ueda from Purdue. Undergraduate from Columbia, where he worked with Breslow, PhD with Jacobson, and then began really the springboard to his career in organometallic chemistry was his postdoc with Jonas Peters, and has been at Purdue since 2013. And he's been heavily involved in this emerging field of bimetallic catalysis. One example from his group is shown here. He looks at a series, and this is the Dalton transaction paper. He looks at a series of isostructural dinickel, dicobalt, and diiron complexes, and shows that these can undergo bimetallic octave addition to electrophiles such as al chloride here. And so this is a case kind of like this bottom example, but you can imagine it's like the bottom example, but where the ligands on the metal actually keep the together, if that makes sense. Keep the overall complex together. So Chris has looked extensively at these naphthyridine type ligands with pendant imine arms. And so that's a really beautiful example of each of the metal oxidation states is increased by 1. And then in this case, both of the organic fragment or the organic fragment and the owl and the chloride bridge both metals. Now it's a little bit more complicated than just that, because one of the features of these ligands that we'll talk about in the ligand design lecture is that the ligands themselves are redox non-innocent. That means that depending on the metal involved in the oxidation state, you can store unpaired electrons on the ligand. So it makes oxidation state determination of the metal itself a little bit non-trivial. So we won't go into all of those details, but just remember this concept of redox non-innocence, and then we'll come back to that. Another example, now a heterobimetallic case, is from the lab of Neil Mankad, and this reference is the top one. And the overall transformation might look somewhat familiar as a non-directed CH borylation that you might associate with developments from the lab of John Hartwig as one of the key contributors, as well as others. Traditionally, this is done with iridium catalysis, but using this heterobimetallic design with a copper iron bond. So this moiety on the left, people refer to as FIP. So this copper FIP complex can promote non-directed CH borylation now where both metals are base metals. So this is a nice sustainable potential solution to CH borylation. And the key transition state involved for this bimetallic oxidative addition is the four-membered transition state shown here. Okay, let's talk now mechanisms. So we've talked categories of reagents that can engage in oxidative addition. Now let's talk mechanisms. One mechanism is a concerted process. And if you like pushing arrows, I can help push arrows here. And the concerted process, as I alluded to, is common for nonpolar substrates. There's relatively minimal charge buildup in the transition state. Normally, formation of the encounter complex between the metal and AB is the rate limiting part of this sequence. And so that's why you often will see second order kinetics, because formation of the counter complex is what's rate limiting. The transition state shown here is a 3-center 2-electron transition state with side-on approach of the AB molecule. The reaction is stereospecific for introducing the A and B cis to one another on the metal. Now, an interesting caveat to that is that in the final product, they don't always end up being cis. So a classical example is if you take some triphenylphosphine ligated palladium, like tetrakis triphenylphosphine, and you add an aryl iodide, it will give you the trans product. Why is that? Because it initially forms the cis, and then you have a geometric reorganization to the trans. So the initially formed adduct should always be cis addition, but then isomerization processes can give you the trans. If you, let's say either A or B is a carbogenic substituent with a defined stereochemistry, then the process will be stereoretentive at that carbogenic substituent. As we said before, we need an open coordination site on the metal, and then we need an open coordination site adjacent to the site where AB is coordinating. And then because there's minimal charge buildup in the transition state, these reactions end up being insensitive to the dielectric constant of the solvent. And so that can be a mechanistic tool that you can use to diagnose whether a concerted mechanism is operative. So if we consider as a representative case study, oxidative addition of the nonpolar molecule dihydrogen, we know from consideration of the MO diagrams that the interactions, when you form a sigma complex, the interactions between dihydrogen and the metal involve a sigma donating interaction, where a filled sigma orbital from dihydrogen coordinates to an unoccupied d orbital on the metal, such as the dz squared orbital or the dx squared minus y squared orbital, and then a filled orbital on the metal, such as the dxy, dyz, or dxz orbital from the metal donates electrons into the sigma star antibonding orbital on dihydrogen. And then when you take that to the extreme, that's when you get HH cleavage. So some of these details about bond lengths I just copied from a previous slide, so we have it all in one place and we're oriented. So this, in the case of the sigma complex, you can get significant bond lengthening, and then the extreme case is that bond is ruptured. And often, in point of fact, this process can be reversible, so you can oxidatively add the dihydrogen and then you reductively eliminate it to form a sigma complex. You can actually monitor this process when it is reversible using some specialized NMR techniques. Okay, now let's consider another mechanism, which is a nucleophilic mechanism, sometimes called the SN2 type mechanism. And so if we push arrows here, now we have d orbitals from the electrons flowing to the AB molecule, rupturing the AB bond. Now you have significant charge buildup in the transition state because the B group is being lost as B minus, B anion. So you actually have a well-defined intermediate where B minus is lost, and then recombination of B minus to the metal A adduct gives you the final product. Again, increase of oxidation state by 2, but now because of the stepwise nature of this process, you're not beholden to cis stereospecificity. So we see nucleophilic mechanisms as being common for polar substrates, where B is a good leaving group. So think things here like methyl iodide. This process, because of its resemblance and mechanistic overlap with an SN2 reaction, is stereoinvertive at the carbogenic substituent. It often ends up with the groups adding, the A and B groups adding trans to one another. As we said, the transition state is highly charged, and thus the overall rate can be highly dependent on the solvent dielectric constant, as well as the ligand environment of the metal. As one might expect, the better leaving group that you have, the faster the reaction goes. That's what's summarized here. And you will see this contrasts to another type of mechanism, which is a radical mechanism. And this can also be used as a diagnostic mechanistic tool. And just like with an SN2 reaction, when you go from this series of methyl to ethyl to isopropyl, the displacement becomes more and more sterically encumbered and the process becomes slower. So a lot of the similar trends that you're comfortable with from SN2 reaction, we see again here. So let's take a look at one particular case study. This series shown below, where we're going to consider nickel 0 with several different coordination environments. And let's just say this is undergoing oxidative addition to methyl iodide as a representative polar electrophile. We see that the reaction is fastest with alkyl phosphines because of their sigma donating properties. That makes the metal maximally electron rich. When we step off that and switch to aryl substituted phosphines, now the metal is not quite as electron rich, so the rate is attenuated a little bit. Then when we start adding one or more pi accepting ligands, such as alkenes, we see that the reaction rate is decreasing and decreases further when we remove all the phosphines together and get to nickel cod. So a caveat here that I'd like to point out is that depending on the structure I have drawn, these complexes will require dissociation of one or more ligands to get to the active form that will undergo oxidative addition. But this trend overall still holds. And COD, if you're not familiar with this ligand, is very common in organometallic chemistry. It's 1,5-cyclooctadiene that I've drawn in stylized form here, but if you want to draw it in more common way, you can draw that. Okay, so now let's consider with the remaining time that we have, the case study here, where we're going to take this iridium carbonyl complex and expose it to two different electrophiles in two different experiments. I shouldn't say electrophiles, two different reaction partners in two different experiments, one being H2 and the other being methyl iodide. And then we'll walk through what the outcomes of this are. And first, I want to ask if anybody recognizes this complex. It's a named complex with a rich history in organometallic chemistry. I hear some whispers. Vasca's complex. Named after Lori Vasca. This is the original publication in the 1960s. Vasca's complex is an interesting case study because it itself is not that useful in catalysis, but its utility comes from the fact that it has this embedded carbonyl ligand that can serve as a nice mechanistic readout for the coordination environment around the metal and how electron rich and how electron poor it is. So this is like the beacon that's reporting back what's happening in terms of reactivity. So let's quickly do the electron count on this, and then we'll compare how this electron count and compares how this looks in the products. So it's a coordination number 4, oxidation state. Someone can just shout it out. +1, that's D what? D8, and then the overall electron count, 16 electrons. Okay, now let's consider that H2 oxidative addition. It's 16 electrons, so that means it can form a sigma complex with H2. And as we saw before, formation of this encounter complex is the slow step, and then subsequent oxidative addition is fast. So Madison, since you volunteered for the first part, what do we think the product of this is going to be in the top case with H2? And specifically, help me think through what the stereochemistry of this. It's a nonpolar reagent. Benji is doing sign language at me. You want to provide an assist, Wenji?
It's non-polar, and I guess after the HH bond ruptures, the two hydrogens will be placed cis to each other.
Okay. And then where's the,
I guess it's that the two triphenylphosphines are pretty full, so that they won't be placed in cis.
okay, you want to keep the triphenylphosphines opposite to one another, which I think is a good thing to have in mind. And then you're going to end up moving the chloride. The other point to consider here, so the sterics of the triphenylphosphine is one consideration, and the other is that as the trigonal, sorry, as the square pyramidal encounter complex is reorganizing, one of the ligands needs to start pointing down, and it's got to be the CO, the phosphine, or the chloride. And that geometry starts to resemble trigonal bipyramidal. We remember that trigonal bipyramidal around the equatorial positions is where there's the most pi basicity. So the pi withdrawing ligands, those that have pi withdrawing character, pi accepting character, want to stay pseudo equatorial there. Okay, and then the bottom case, we have methyl iodide.
Polar, so it'll probably include like
It's polar.
probably add to the methyl tricopyr iodide and then convert it to the iodide trans.
Okay, and then how about the electron counts for these two medicines? Oxidation state is what?
Still. Okay.
The 6 you said, I think, and overall was what? And then just to keep things on track, we'll say ditto for the next example. So this shows some of the changes that take place. You go to a higher coordination number in this 16 electron case. You go to higher oxidation state. The d electron count goes down, and the overall electron count goes up. In the case of a 16 electron complex, starting material, if you have an 18 electron complex, you won't go up to 20. Maybe I'll just introduce this last one. I know I'm a minute or two over, just to kind of wrap up this discussion. There are, and then the third canonical pathway for oxidative addition is involves open-shelled species. So this is a radical oxidative addition mechanism. For those who are involved in radical type cross couplings, this will look very familiar to you. And there are two flavors of radical oxidative addition: chain mechanism and non-chain mechanism. And those are depicted in general sense here. So let's see if I dare try to push electrons. Now we have the fishhook arrows. The non-chain pathway results in first formation of a metal, typically halide, metal halide bond, and then typically alkyl radical that then recombines. So you have stepwise addition of your, or stepwise increase of your oxidation state from M to M plus 1 here. And then you have also a chain process where an alkyl metal can engage with typically a closed shell, well, I shouldn't say that. Alkyl radical can engage with the metal to generate now typically an open shell metal species with radical character, and that can then form a bonding interaction with typically halide and generate the or a dot that then can find another molecule of the metal organometallic species. In both cases, you ultimately get to the M+2 product. This radical pathway can be operative either with polar or non-polar coupling partners. Some diagnostic features are that now, because a radical species is involved, if you have stereochemical information at the carbogenic group, that will be eroded through racemization of the radical. Because it's a radical process, it follows trends of radical reactivity. So you have increasing rate as you go methyl, primary alkyl, secondary alkyl, tertiary alkyl. And then a difference that I'll highlight between the SN2 type pathway and the radical pathway is that in the SN2 pathway, tosylate is a very good electrophile. In the radical pathway, it's a poor electrophile. So you can use that as a diagnostic mechanistic tool as well. We talked about how first row metals are of the three rows, first row are the happiest to have unpaired spin, and they're the happiest to engage in radical oxidative addition. And then just one quick case study of a non-chain pathway. I had said that this is most common with first row metals, but it's not exclusive to first row metals. So here's a case of platinum, phosphine ligate of platinum undergoing a radical-based oxidation process. So the sequence here is first loss of the phosphine ligand, and then if you want to push arrows, hemolysis of the alkyl X bond to generate an alkyl radical, which can then recombine with platinum. These are the coupling partners that were looked at in this study. So I'll leave it to you based on what we just said to predict what the order of reactivity of that series would be. Good. So I think we'll stop things here for the minute, and then on Thursday's lecture, we'll wrap up other elementary steps. We'll try to get through most of it. We might have one section that needs to carry over to next week, but we'll try to wrap up as much as we can. And then for those, if anyone walked in late, reminders are Wikipedia topic. Send that to myself, Mathieu, as soon as possible, and then look forward to homework and office hours. Thanks, everybody.